それではまず1校目の皆様をご紹介いたしましょう。1校目はシンガポールのファーチョンインスティテューションからお招きいたしましたシェ・ジンカンさん、ジン・ケインシアン・アレンさん、そして指導はアン・シュンフン先生です。それではお二方どうぞよろしくお願いいたします。
こんにちは、皆様。I am Jin Kang.
I am Alan.
Today, we are very honored to be invited to present more about our project. But first, let us introduce our country, Singapore, as well as our school, Hua Zhong Institution. Behind, we see our national flag.
First off, Singapore comes from the Malay language. It comes from the Malay word Singapura, which means Lion City.
Now, how far is Singapore from Nagoya? We took around 7 hours of flight to get here.
Singapore is extremely small. It is about 500 times smaller than Japan. Singapore has a relatively large population of around 6 million. We are also multiracial, meaning we have many races, including Chinese, Malay, Indian, Eurasian, and many more.
Now, let us introduce you to our school, Hua Zhong Institution.
Our school will be turning 100 years old next year. We will be holding a big celebration then.
One famous spot in our school is our clock tower. It has been recognized as a national monument and has been featured in our Singapore stamp.
Students in our school undergo a 6-year program covering both junior and senior high schools. We have around 3,000 students in our school.
Now, let us introduce you to our project, which is called Ruthenium Arene Complexes with Anthracene Shao-Kun ligands.
Firstly, what are ruthenium arene complexes? As you can see, there is a ruthenium atom located in the center of the complex, covalently bonded to 3 ligands. Also, there is an arene group attached to the top of ruthenium.
But why did we choose ruthenium arene as our project? That is because ruthenium arene has a rather high yield, is relatively safe to synthesize, as well as being very stable.
Now, we know that ruthenium arene complexes kill cancer cells. However, the current problem with ruthenium arene complexes is that we do not know how they kill cancer cells. So, current hypothesis regarding this issue is that ruthenium arene complexes targets either DNA or proteins.
Now, our aim is to find a suitable method to track our ruthenium arene complex within a cell. Now, our proposed method is fluorescence, and the reason for so is that fluorescence is effective, cheaper than other methods such as nuclear medicine, as well as less toxic.
Thus, the aim of our project is to investigate how ruthenium arene complexes kill cancer cells by linking a fluorescent molecule to the ruthenium arene and tracking it in a cell.
Our fluorescence tracker will be anthracene, which has a structural formula shown there. It's a widely known fluorescent organic compound.
But first, we have to find a way to link our anthracene to ruthenium arene to achieve fluorescence. Shell cones can be used as this link. Shell cones are found widely in the plant kingdom, and its structure can be modified to include the anthracene group from the benzene group here.
Why did we choose shell cone? Similar to ruthenium arene, it has a rather high yield. It's also safe to synthesize and easy to synthesize, as well as displaying a wide variety of biological activities, such as being antibacterial, anti-inflammatory, and anti-tumor.
Thus, the aim of our project is to link the anthracene to the ruthenium arene via a shell cone moiety. We will be synthesizing such molecules and their isomers for fluorescence imaging. Thus, we hope to use fluorescence imaging to possibly track their mechanisms of action.
Let us talk about our first complex synthesized, 2A.
Firstly, we synthesized dichloropycimene ruthenium 2 dimer as well as chalcone 1A using the outdoor condensation method. Next, we use these two products as further starting materials to synthesize our desired compound 2A.
For our procedural steps, we first dissolved all of our chalcone 1A in dichloromethane before adding in our dichloropycimene ruthenium 2 dimer. This reaction mixture is then refluxed for 12 hours. Then, a rotary evaporator is used to remove most of its solvent at reduced pressure. We then recrystallize to obtain our pure crystals from our solution.
After obtaining our product, we needed to run it through a series of characterization tests to verify its presence as well as its purity. Firstly, we ran the mass spectrometry test. As you can see, we expect a mass over charge ratio for our compound of 615. But what we observed there is a mass over charge ratio of 580. This difference can be accounted for because of the loss of one chlorine atom from our compound.
We have also completed infrared spectroscopy tests. In this infrared spectrum, we can see a peak at the wave number of 1662, which is correspond to the C double bond O bond there. Now, for our final complex, we can see that there's also a peak at the wave number of 1666, indicating that there's still a presence of the C double bond O group.
Lastly, we ran the nuclear magnetic resonance spectroscopy. This was the spectrum that we have obtained, and we can split it into two sections. The first section is for the arene. We have successfully assigned the protons according to their colors. The next section is the section for the chalcone. We have also successfully managed to assign these protons as shown here.
Now, we will be talking about the second product that we have synthesized, which is an structural isomer of the first, and we will be explaining it later. Now, similar to our first chalcone, we synthesize a structural isomer of that using the same method of aldol condensation. As you can see, the difference is where the C double bond O group for our 1A is closer to the pyridine, but now it's closer to the anthracene side. We then react it similarly with our dichloropycimene ruthenium 2 dimer to obtain our final complex 2B.
Just like complex 2A, we also ran the same characterization test to verify the presence and purity of our complex. For our mass spectrometry, we have obtained similar results.
We have also confirmed the presence of the C double bond O group, albeit a different wave number for both 1B and 2B.
Lastly, for our nuclear magnetic resonance spectroscopy, we have also managed to assign similar protons.
Now, for our future work, we talked about fluorescence at the start, and we have successfully synthesized both of our compounds. So our next step is to use the UV-vis spectrometer to obtain the excitation wavelength of our compounds. Using a fluorescence spectrometer, we then can obtain the emission wavelength of all of our compounds using the excitation wavelength obtained earlier.
In summary, we have successfully synthesized and characterized complexes 2A and 2B. The next step would be to test if chalcones and complexes are fluorescent. If they are fluorescent, then fluorescence imaging can be used to track their mechanisms of action. Now, what does this imply? This implies that once we know the mechanisms of action of ruthenium arene complexes, we can then design more effective ruthenium arene complexes in future. This improves our combat against cancer.
So we would like to thank everyone that has made our trip possible, and we hope to invite all of you to Singapore in the near future. Arigato gozaimasu.
ありがとうございます。それではご質問の時間へと移らせていただきたいと思いますので、ご質問のある方、挙手をお願いいたします。はい、では後方の方にマイクをお持ちしますので、お待ちください。
Hello, I've been asking questions for so many people, so I decided to do it to you too. So, I've been doing synthesis of esters for quite a long time, and there seems to be some similarities in your reactions as well. Right here on the first substance, which one is it? The pyridine 4 carbaldehyde? You're trying to make this one, right? Now in here you're using the sodium hydroxide as a catalyst. What is the reason for this substance?
So, because this reaction is known as the aldol condensation, it's quite important for the base to always be present. So, here we have a few steps. Okay, a few steps where aldol condensation occurs. Now, the most important thing is that the hydroxide group of our base, it doesn't have to be sodium hydroxide. It could be potassium hydroxide, let's say. But the OH minus group must be present to attack one of the hydrogens bonded to the carbon. So after it attacks that hydrogen bonded to the carbon, it will form water, and we will be left with a carbon that's actually negatively charged. Now, once the carbon is negatively charged, it will then act as a nucleophile to attack the next carbon, which is on the other side. And once it attacks that carbon, we will have an intermediate product, which has 2 oxygen in it. And once it attacks the next carbon, and it forms that, then the electrons would then force the O double bond C in one of them to become a O single bond carbon. And once it reaches a O single bond carbon, the water, which may not or may be the same water that was produced at the start of the reaction, would then, the water will then, the OH minus will then attack the hydrogen of one of them to give water. And once the hydrogen is attacked, the electron goes back to the carbon, and the carbon will form a double bond with the next carbon. And by doing so, at the same time, it breaks off the O single bond to the carbon where it has already formed a hydroxide.
So the hydroxide ion is necessary for this reaction. I thought I would propose a different kind of base, but judging from your reaction, looks like it is unnecessary.
The base is, as long as hydroxide ions are present, the base does not really matter.
I thought I was going to propose you a base which name is triethylamine, but they don't really contain the hydroxide ion, so yeah, that's what I wanted to ask. Thank you.
よろしいでしょうか。ありがとうございます。その他ご質問のある方いらっしゃいますでしょうか。はい、では松坂先生お願いいたします。2列目でございます。
A very nice talk. Okay, so fluorescent, so Anthracen unit and pyridine unit. In your ligand, Anthracen unit and pyridine unit are linked by alpha, beta, and saturated carbonyl moieties. So why don't you directly bind the Anthracen unit to the pyridine moiety?
We have considered this before, so let's go back all the way to why we designed this complex. So the first of all is that while it may not seem important, ease of synthesis is actually a rather big criteria for us. So we have obtained a research paper that has synthesized our Xiaokun with the Anthracene before. So it's rather easy for us to confirm that there will be a reaction between with the dichloropyrimidine ruthenium 2 dimer to the Xiaokun. Well, as you said, it could be possible for us to link the Anthracene directly to the pyridine. But then we have some other factors and some side effects that we may not have taken into consider. Another idea that some people may have asked would be, if we are tracking ruthenium arene complexes, why not just link the Anthracene directly to the ruthenium arene complex right on top of it, so we can skip the entire Xiaokun part? Now, we have seen a research paper that have done exactly so, but it has been seen that the ruthenium arene properties have somehow been shielded, somehow been modified, such that it's not so powerful anymore.
ありがとうございます。それではお時間になりましたので以上とさせていただきます。バーチョンインスティチューションのお二人でした。どうもありがとうございました。Thank you very much.